Hello everyone, my name is Janis Erdmanis and today I will present the package ShuffleProofs.jl to make zero-knowledge proofs of shuffle for re-encryption mixnets, often used in e-voting systems. In our daily lives we often use cryptography in situations where we can't trust the other one to do the right thing, whether this is e-commerce, a bank, or a cloud service. If conflicts arise, we can resolve those with the help of the state institutions. But when the state is at the stake, as in remote electronic voting, the end can no longer be trusted. And we need to find new ways to combine privacy and accountability, known as the e-voting problem. Ironically, the problem of e-voting boils down to efficiency. Privacy is hard because of large amount of data can be copied instantly or silently collected during the casting procedure, whereas accountability is hard because of the ease at which it is to manipulate data at scale without leaving any traces. Thus only relying on software auditing is never an option. In e-voting system designs, privacy is often achieved by employing a mix cascade. As long as one party managing the mix is honest, the link between the voter and the vote remains secret at all times. However, as we introduce more players to the game, we make it easier for an adversary to come in and manipulate the election result. One way to get out of this security nightmare is to make parties accountable with zero-knowledge proofs of shuffle. In particular, the Wikström-Terelius variant for proof of shuffle, as implemented in Verificatum, stands out as being the most widely used, and in addition, it is patent-free and licensed under a permissible MIT license. Nonetheless, I was not at all eager to jump into the Java ecosystem to use it for my doublings in e-voting system designs. Instead, I wanted to have a lean, modular code base, which is easy to set up on any system, delegating worrying about compatibility issues to a programming language designers. Thus I saw Julia a perfect fit. However, a major downside of Julia is that it lacked libraries in public key cryptography. Thus, before even I could start with proof of shuffle, I had to implement cryptographic groups, hence the CryptoGroups package was born. To see it in action, let's initiate a modular prime group with modules 23 and order 11 that we can do using pgroups constructor, where the first argument is prime modules and the second one group order. This resulting object G is a group type, with which we can initiate group element, lowercase g. By taking powers of G, we can see that it generates 11 different group elements as expected, and for G elements throws an error for safety reasons. Thus, G is generator for the group. With this level of abstractions, we can implement many different cryptographic schemes like digital signatures, Diffie-Hellman key exchange, ElGamal crypto system, and as well as zero-knowledge proofs, including the proofs of shuffle. But before we can move into the proofs of shuffle, we need to recall the basics of ElGamal crypto system. For example, consider two parties, sender and receiver, where the latter generates secret and publishes a public key. In ElGamal, the sender chooses a group element M freely, which is his message, and encrypts it with secret randomization factor R, forming a tuple A-B, which holds an encrypted message as shown on the slide. To decrypt, the recipient multiplies B with inverse A, raised to the power of his secret key. What differentiates it from an ordinary public key encryption scheme is that it is possible for a middleman to re-encrypt the ciphertext while still preserving the message when it is decrypted, as shown on the slide. That is often used in the mixnet setting, where receiving multiple messages can be re-encrypted and shuffled, breaking the link between input and output, while keeping the encrypted messages intact. To see it in practice, let's look at typical re-encryption mixnet voting system pipeline. In this example, messages m equal 5 and m equal 7 correspond to votes for candidates A and B. Each voter picking their favored candidate then encrypts message m with a randomization factor and submits that to the mix. The mix re-encrypts each message and forms a shuffled output that is further passed to the decryptor, which decrypts the ciphertext and outputs votes, which then finally can be counted. The issue with this setup, however, is that we need to trust mix and decryptor to act honestly and not to spoil or replace votes with their favorite ones. One way to prove an honesty of the mix is with re-encryption randomization factors. In ShuffleProofs, those are generated when shuffle function is called with ciphertext generator and public key. The output is proposition containing all mix inputs and outputs, and secret containing randomization factors as shown on the slide. Then one can keep the mix accountable by calling a verifier method that would only return true when the mix had acted honestly. The problem is that if this evidence were published for everyone to access, it would violate privacy, making the mix a meaningless addition to the pipeline. Fortunately, we can do better with the help of non-interactive zero-knowledge proofs of shuffle. This allows us to prove that verify method returns true without revealing secret inputs, in this case the randomization factors. The ShuffleProofs is a library which can make such proofs. How to do it? We first initiate a verifier with protocol spec constructor, to which we could pass multiple cryptographic parameters that need to be chosen with care. Here, for the sake of demonstration, we shall use the default values. Then, having a verifier, we can construct a proof by calling a proof method with proposition, secret and verifier. For convenience, the proof can also be constructed by passing verifier to the shuffle method as shown. The beauty of this approach is that the proof can be published for everyone to verify the honesty of the mix without compromising privacy. A similar proof can be made for honest decryption, which is something yet to be implemented. From a technical point of view, ShuffleProof closely follows Verificatum verifier specification up to a level that you can take a proof generated by Verificatum and verify a proof of shuffle part with ShuffleProofs.jl. Vice versa in principle also should work, though not yet tested. In addition, as the verifier is implemented as finite state machine, deviations from Verificatum verifier specification can be easily supported. So, at the moment, ShuffleProofs, together with cryptogroups, can be used to tinker with different e-voting system, e-voting and e-voting related designs. It is easy to set up running on any machine, which could be interesting for educational purposes. However, it is not yet close to being a drop-in replacement for Verificatum, as the performance and security is lacking, and many features are missing. But to make matters better in the future, I plan to focus on adding Verificatum compatible proof of decryption, adding command line interface, and that's already would cover many cases of Verificatum use. Add docs for an improving performance for cryptogroups and also interfacing existing cryptographic libraries with cryptogroups API to make ShuffleProofs even more performant. Also, I plan to tinker with e-voting system designs in Julia, where proof of shuffle takes an integral part. To learn more on what I have been working on, go to peacefounder.org, where I provide more detailed exposition. And this is all. Thank you for listening to my talk, and see you in the chat.